Let us then take the case of a convex mirror. So we're going to draw in our line of action, our neutral axis. We're going to draw in our line of action, and then I am going to draw in my mirror. Convex. So the first going to be on that side. So I've set this up. So DO is equal to 10 centimetres. We'll get into F, HO, the height of the object is going to be 4 centimetres. Just check. Yep, 4 centimetres. And what we're going to do is we're going to put F at 5. But the difference between a concave lens and a convex lens is a concave lens, we put the focal point on the side. For a convex lens, it goes on this side. So if I'm going to put the focal length in for a convex lens, it will go here. So F is equal to 5 centimetres. But what I've actually done is I've made, because it's on this side for a mirror, I'm going to make that minus. And then we're going to do the basic thing we did before. So the ray 1 goes parallel, then through F. So what we do here is it goes through about there. The ray goes parallel, leaves the object, goes to the mirror, parallel. Boink. And then it hits the mirror, and it will reflect, along line, similar to what we did the other ones. If I put this ruler so it touches F, and it touches this point and F, so I put the ruler there, so it's going to touch F and the bounce. It's going to reflect up that way. So the line will actually go physically, bing, bounce. And then we do the second line through F, then parallel. So the second line, what we'll do is we put the tip of the arrow there, the ruler on tip of the arrow and F, and I'll draw it down until it hits the mirror. And then it physically hits the mirror, yeah, and then it's going to reflect, bounce. So it bounces parallel. Now, the question is, are these two lines ever going to meet? And the answer is no. So just like we did with the concave mirror, one of the cases there, what we're going to do is we're going to backtrack the reflected lines. So we look at the line that reflected, it bounced. I'm going to backtrack that down to F. And because it's only a reflection, I'm going to put a dotted line in. And then this one comes down here, bounces parallel, so I'm going to backtrack that line onto the other side of the mirror. And again, we're going to use a dashed line. Where those two meet, that's going to be where my image is. So ask the same three questions we did before, upright or inverted. And looking at this, the image is upright, enlarged or reduced, Well, we look at this and we can see that that's smaller than that, so it's reduced. And in fact, for a convex mirror, it will always be smaller. That's why films like Jurassic Park, it says, objects in the mirror may appear bigger, because they're looking into a convex mirror. And then the answer to the question is real or virtual. Can we project this onto a piece of paper? So these will never meet. Where they meet is dashed lines, so that's going to be virtual. So then we want to pick up two more pieces of information. DI HI and magnification. Or we can just measure DI. DI, so it's going to be DO, so it's going to be DI. DI is going to be, what's that, 3.3 centimetres. HI is going to equal 1.5 centimetres. But, well, we can use math. So we can use our formula that we've used for all of the others. F -1 equals DO -1 plus DI -1. Now I want to find out DI, so I rearrange that. DI -1 equals F -1 minus DO -1. So then we go DI is equal to F -1 minus DO, all to the negative on. So we stick in numbers, so F is going to be, let's do that, F is going to be, and this is the important thing, we've got to stick in -5 minus DO 10, -1, and we take all that to the -1. So, but the important thing is here, because the focal point is on this side, this is a negative number, we must put a negative number in there. And we can do it, we just stick in the calculator, -5 to the -1, minus 10 inverse equals, take the square root, take the inverse of that, equals -3.333 centimetres. Basically, the negative says that the image is going to be on this side. So that was pretty good. And what's the height? Again, we can use similar triangles. Height image of a height object equals distance image of distance object equals, so height image times HO times HO equals HO times DI of DO equals distance 4 centimetres, 4 times DI 3.333 over DO 10 equals 4 times 0.3333 divided by 10 equals 0.1333. And the final thing is magnification. Magnification is equal to HI over HO. It's also equal to DI over DO. So let's use that one. So M is equal to, DI is equal to minus 3.3 centimetres. 3333 over DO, which was 10, equals minus 0.3333. So it says it's a third of the height. Magnification is 1/3. This is a third of the size of that one. The negative sign just says it's upright. Life is good. So again, these are tricky when you're doing these ones because you have to take into account the focal point is on this line, because when you reflect the rays, they're diverging, they'll never meet. We have to backtrack them onto this side using dotted lines. That tells us it's a virtual image. And when we're doing all of these, when we're using the standard equations, when we're doing the math, we have to use negative number for the focal length. If we do that, the maths will come out fine.